Yeah, so let me start with a little bit of history and what we can learn from the history of quantum computing. So quantum computing is usually dated back to Richard Feynman, who in 1980s made this great observation that, well, it's difficult to model quantum physics on an ordinary computer, and maybe that's actually an indication that you can use quantum physics to build better computers. And originally, quantum technologies were the domain of a very small number of crazy scientists. Number of people working on it was very small, and these people were often very far outside of what was considered the scientific mainstream of 1980s. So, for example, the quantum cryptography, as we know, goes back to a scientist called Stefan Wiesner, who wrote his first papers on quantum states and quantum cryptography in late 1960s. And back at those days, this topic was so unusual that his papers got rejected for publication once, twice, third time. He had real difficulty publishing his ideas because those ideas were too unusual. And in one of his first papers, he proposed this idea of using quantum to build an unforgeable subway tokens. So what he was interested was using quantum states to build unforgeable quantum money, but he could only make quantum money what could be used only once, and he called it unforgeable metro tokens, like tokens that you can use when entering metro, and then the machine eats the token, and then if it's one-time token, there is no need to reuse it. So this was his idea. It was a very unusual idea. It was a heavily impractical idea because subway rides cost about $1 or $2, and it's not worth to build quantum tokens for them. So these ideas had real difficulty gaining acceptance, but what turned out is that the same mathematical ideas, on them one could build today's quantum cryptography. And today's devices for quantum key distribution that colleagues from Latvian Radio and Television Center are connecting into a secure quantum network, they essentially go back to these ideas of Stefan Wiesner, with mathematics being used in a slightly different way for a different application. And the same things happened with quantum computing. Quantum computing, as we know, dates back to an eccentric scientist from Oxford, David Deutsch, who saw these ideas of Feynman, and then he developed a toy problem which could be solved in 2 steps on a conventional computer and 1 step on a quantum computer. And again, this had real difficulty gaining acceptance in scientific community because, so what? This problem is so trivial that it can be solved in 2 steps on a conventional computer. What's the benefit of building quantum computer to solve it in 1 step? But again, what happened is that this was a beginning for a chain of research results that was getting bigger and bigger quantum advantages. And this culminated with the discovery that quantum computers could actually break most of today's data security. And the origin of that, at the beginning of that was this problem which could be solved in 2 steps on a conventional computer and 1 step on a quantum computer. So what can we learn? I think one thing that we can learn is the importance of highly out-of-box ideas. So both quantum cryptography and quantum computing started with ideas that are highly extraordinary, highly out-of-box. And initially, the first scientists who were working on them were not solving practically important problems. They were solving artificial problems, but since they were using such highly extraordinary ideas, it later turned out that these ideas can solve many really important practical problems. And the second important point that I want to make is that algorithms and applications are what drives the development of quantum computers. So the fact that we can use quantum computers is what makes the humanity to build them. If we didn't have algorithms for useful problems, there would be no reason to build a quantum computer. And speaking of applications of quantum computers, they come into two categories. So one big category is quantum computers for quantum physics, for quantum chemistry. This is what is called quantum simulation, simulating molecules on a quantum computer, roughly. The ultimate application could be drug design. The ultimate application could be better batteries or better industrial processes in chemical industry. And with quantum simulation, the key thing is that simulating quantum systems on a conventional computer is very hard. It takes a lot of resources of the world's best supercomputers. It's probably the second most important application of supercomputers after artificial intelligence and machine learning. Quantum computers could make it much faster and much more precise. And because of that, quantum computers have potential of revolutionizing a lot of areas in physical and chemical sciences. Chemical processes are essentially described by equations of quantum physics, so what can solve the quantum computer. And then this would have effect downstream on all the areas that use physics and chemistry. And as a computer scientist by my origin, I'm interested in the second class of applications, how to use quantum computers to process data better, whatever these data are representing, whether it's a data describing a social network or whether it's an image data. The common thing is that we have some data that we process on our conventional computer, and then we want to do it better on a quantum computer. And one major theme in data is searching large search spaces. A search space can be a phone directory. A search space can be a scheduling problem where we want to find the best route for a truck. In this case, there is a lot of possible routes, and we are searching for the best route among many possibilities. Search problem could be breaking a cipher. Then again, we are searching among a lot of keys for the cipher for the right key. And yes, search problems come up in machine translation and artificial intelligence. We could be searching for the best translation for a sequence, sentence, or something like that. So in all of those areas, we have search problems, and many of them are amenable to better quantum solutions. And on a technical level, we have a lot of quantum tools for search. So the first quantum search algorithm was developed in 1996 by another unusual scientist who liked working on out of mainstream topics. And since then, we have developed a number of better search algorithms for quantum computers. Yeah, so here is one example. This is an example of our work. I tried to make it as non-technical as I could. So there is this thing in search which is called search by backtracking. And this is one of those core computational tasks that are running in the background on your computer without you ever noticing it. It's used for AI, it's used for natural language processing, it's used for scheduling, it's used for a lot of other things. It basically solves an abstract search problem, which is a backend for many practical problems. So, for example, in natural language processing, one might solve the problem of finding the right translation or understanding the meaning of a question by translating it into a set of logical constraints and then using search to solve this system of logical constraints. And in the search by backtracking, we are trying to solve a problem by building up a sequence of partial solutions. And if at some point we get stuck, we backtrack, we return to the previous step. And if we get stuck again, we return one step more back. And in this way, we search all the possible solutions to a problem. And what we have done is, so here is an example. We may be solving some system of equations, and in this case, each step of a solution is finding a value for one variable. So we first try a value for first variable, then we try a value for second variable, and then if it doesn't work, we step back and try something again, something else. And we can solve this problem by a method called quantum walk, in which we design a quantum process on the space that we are searching. So in the memory of quantum computer, we have this space of possibilities that we want to search, and we make the quantum computer to imitate a quantum particle that is moving around on this space. And in this way, we can solve this search task quantumly better than we ever could it on a conventional computer. And then a second thing for which quantum computers are good, they are good in linear algebra, because quantum mechanics on a mathematical level are linear algebra. So quantum computers could solve huge linear algebra tasks in a very short amount of time. Essentially, if we have a quantum bit, elementary unit of a quantum bit, it's described by a matrix consisting of 2 columns and 2 rows. And if we have a system of, say, 30 quantum bits, it's described by a matrix that consists of 1 billion rows and 1 billion columns. So what it lets us do is we can encode our problems into algebra, into matrices. And then we can perform these matrices on a quantum computer and solve the problem in an instant. So essentially, if a conventional computer has to operate on really big matrices or really big algebraic objects, it needs a lot of time. Quantum computer could do it in an instant. Yeah, so what we can do is we can solve huge systems of equations in a moment. Well, under some assumptions on what systems we want to solve and what type of solutions we want to get. And then this could be applied to many areas where equations and matrices come up. And in particular, one area where this could be useful is machine learning and artificial intelligence, which is very hot these days. So in machine learning, a lot of things are based on large language models, and a lot of resources goes into training language models. And in this training process, there are steps that we can view as quantum linear algebra and do better quantumly. So we can take steps in training machine learning model and do it more efficiently quantumly. And quantum computers are quickly turning from a theory of algorithms into something that one can touch and one can program. There is an ongoing European project of placing 6 European quantum computers into 6 high-performance centers around Europe so that people can experiment with quantum computers. So we are a partner for the geographically closest of these projects, which will place a quantum computer in the leading high-performance computing center in Poland, in Poznań. So there will be a quantum computer with 20 to 50 quantum bits there, and we will serve as a partner for integrating this quantum computer into their high-performance computing environment and testing algorithms on it. And what this computer is it's an example of what is called near-term intermediate-scale quantum computers. So these are quantum devices of a non-trivial size. They have tens of or hundreds of quantum bits, elementary units of quantum computing. They have error rates that are not very small, but not huge either. And on these devices, one can run test computations. These devices are not powerful enough to solve something practical yet, but they are big enough to test ideas and to see the difference between quantum and non-quantum. And to see where we would like to go, here is what a few applications of quantum computers would need. If we wanted to do a useful simulation in chemistry, we would probably need around 100 quantum bits, and we would need to perform maybe about 3 million quantum operations before the quantum device stops. We already have 100 quantum bits, that one we have, but the length of computation that we can perform on today's quantum devices is more like hundreds or thousands of quantum operations rather than these 3 millions that we would need. And there are 2 paths forward. The problem currently is noise. Current quantum computers are very noisy. They can only run short computations before the whole computation breaks down. And the 2 paths forward, one path forward is developing quantum bits with a higher precision. That means quantum bits with precision 1 in a million or 1 in a billion instead of 1 in 1,000 that we have. This is what Microsoft has been working on with its Majorana quantum computer. It's very controversial because it's not clear if they have it or not, but it's their approach. A second approach is that we could use less reliable quantum bits. We could use many of them to fight noise and to store information into a combination of many quantum bits. So this is quantum error correction. We use many less reliable quantum bits to construct more reliable virtual quantum bits. And then this has less requirements on quantum bits in terms of error, but it has bigger requirement in terms of the number of quantum bits. So we either need much more reliable quantum bits, or we need much more quantum bits of the same quality that we have. These are the 2 paths forward. And quantum error correction is actively being pursued. Every time, once in a couple of months, there is some headline about Microsoft or IBM or Google demonstrating better forms of quantum error correction. So all these things are topics of active research. And from perspective of myself as a quantum algorithms researcher, I think that road to practical quantum computing involves a hardware and software part. Hardware part is building better quantum bits. Software part is building algorithms that work on less reliable quantum bits. And this is what we are working on. And lastly, in January 2026, in Riga, we will have the biggest conference on theory of quantum computing. So for a week, Riga will be the capital of the world for theory of quantum computing. 18 to 1,000 scientists are coming here. There will be industry presentations, and yeah, that we are also looking for sponsors. So if you know any organizations interested in sponsoring this event, talk to us. We would be very happy for your help. Thanks.